Hello. This video will be covering Chapter 13, which is going to be discussing gravitation. You probably suspect that you've got at least some idea as to what gravity is all about. Obviously, the gravitational force is what holds us to the Earth, holds the Earth in orbit around the Sun, holds the Sun together with the stars in the galaxy, reaches out across intergalactic space to hold together local groups of galaxies, holds together the local supercluster of galaxies, pulls the supercluster towards the great attractor, attempts to slow the expansion of the universe, and is responsible for black holes. So yeah, it's really not that important, is it? Gravity is far-reaching and very important. Gravitational attraction depends on the amount of stuff an object is made of. Earth has a lot of stuff and produces a large attraction. The force is always attractive. It's never repulsive. It's different from what you might consider to be the electrostatic force, in which you have a positive and a negative charge. This force is always attractive. And just gravitation is the tendency for bodies to attract each other. Newton realized this attraction, was responsible for maintaining the orbits of celestial bodies. And Newton's law of gravitation defines the strength of the attractive force between particles. For an apple and the Earth, we're looking at 0.8 newtons. For two people, we're looking at something less than 1 micronewton. The magnitude of the force is given by F is equal to the gravitational constant times the product of the masses divided by the radius or the distance between them squared. G is going to be your gravitational constant of 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. And the force always points from one particle to the other, so this equation can be written in the vector form. So a uniform spherical shell of matter attracts a particle that is outside the shell, as if all the shell's mass were concentrated at its center. This shell theorem describes gravitational attraction for objects, and Earth is a nesting of shells, so we feel Earth's mass as if it were all located at the center. Gravitational force forms third law force pairs, and in other words, the Earth's force on the apple and the apple's force on the Earth are both going to be 0.8 newtons. You have a diagram over here where this is the pull of particle 1. Let's see if I can blow this up a little bit so you can actually see it. The pull of particle 1 due to particle 2, and then you draw the vector with its tail on particle 1 to show the pulling, and a unit vector points along the radius, along the radial axis. The difference in mass causes the difference in the apple-Earth accelerations. In other words, while the force that you may experience between the two is going to be the same, the accelerations are going to be quite different. Acceleration of the Earth towards the apple will go largely unnoticed. The acceleration of the apple towards the Earth, on the other hand, is far greater, and that's because of the difference in the masses. So a particle is to be placed in turn outside 4 objects, each of mass m. A large uniform solid sphere, a large uniform spherical shell, a small uniform solid sphere, and a small uniform shell. In each situation, the distance between the particle and the center of the object is d. Rank the objects according to the magnitude of the gravitational force they exert on the particle, with the greatest being first. This is, in fact, a trick question. The distance between the particle and the center of the object is always d. That never changes. Each of these weigh the same amount. It's going to be a mass of m. Particle is never going to change its mass. The gravitational constant doesn't change. So the gravitational force, as defined by this, will never change. It doesn't matter what the shape of the object is. That's what the point of this particular exercise comes down to be. So, find the net gravitational force by the principle of superposition. The net is the sum of the individual effects. Add the individual forces as vectors. So the force on particle 1, the net force is going to be the same as just summing all of them from particles 2 to n. If you have a real extended object, this becomes more complicated. And if the object is a uniform sphere or shell, we can treat its mass as being at the center. So we want the forces, pulls, particle 1, not the forces on the other particles. I've been thinking I have missed something here. There we go. So you've got a particle here. It's a mass m sub 1. You have another particle here, m sub 2. You have another one, m sub 3, and they are all certain distances away from particle 1. So we want the forces or the pulls on particle 1 and not the forces on the other particles. So we're not looking at forces being applied this way. We're looking at the forces on this guy right here. The pull on particle 1 due to particle 2, since this is gravity, everything is going to be considered to be attractive. The force of on particle 1 due to particle 2, it's going to try to pull it this direction. The force on particle 1 from particle 3 is going to want to pull it this direction. If you look at the sum of those two, by putting them together in this vector format, you can see that this net forms the hypotenuse of that particular triangle. And this is going to end up being your net force vector, your superposition vector. So let's take a look at checkpoint 2. This figure shows 4 arrangements of 3 particles of equal masses. It's kind of like the problem that we just went through. We're going to rank the arrangements according to the magnitude of the net gravitational force on the particle labeled M, with greatest first. And then following that, in arrangement 2, is the direction of the net force closer to the line of length D or to the line of length capital D. So let's take a look at this and rank the arrangements according to the magnitude of the gravitational force on the particle labeled M. What you are looking for here, since all of these are equal masses, what you are looking to do is to judge the distances that these are from each other. So if you are looking to rank the net gravitational force of this particular object, that net gravitational force is pulling, this object and this object are both pulling on object M, and they're pulling in the same direction. While they have different distances, obviously this one being further away is going to exert a weaker force than this one will, they are pulling in the same direction. it's going to make a net gravitational force that's a little bit stronger. If you start to angle these forces such that you have them at right angles, the force will certainly pull in a direction that's somewhere in between those two, but it certainly won't pull it as hard as it would in this particular direction. It's pulling it one way and it's pulling it this way with masses of 2m. This over here is pulling with some force this way, and it's pulling with a lesser force in this direction. So you'll see some movement, but you won't see quite as much. Same thing is going to hold here. I mean, this and this are, just almost right angles at each other. They're going to exert about the same magnitude of force here. This, on the other hand, in part 3, is going to be the weakest, and it's going to be the weakest because you have mass that's going to be pulling on this in one direction, and you've got this over here, what's a little bit closer, it's going to be pulling on the mass in this direction a little bit more strongly since it's a little closer. They don't work together, they're working against each other. In this particular case, they're working together. That's why that gets ranked highest. These two are not quite working together, but they're not quite opposing each other either. They're working in 2 different dimensions. So you're going to see movement in 2 different dimensions, but it won't be anywhere near as strong. This is it's pulling in the same dimension, all right, but one is pulling in one direction, this is pulling in the other. That's why you get the ranking here in part A that you do. For part B, if you look at arrangement 2, is the direction of the net force closer to the line of length D or to the line of length big D? The reason the answer is the line of length D is, again, look at your definition of gravity. The smaller this value is, the bigger this is going to be. If the masses are the same in the top, the smaller this is, the greater this is. That's why it's going to be pulling a little bit stronger towards this mass than it will be this one, and it's due to the distance. Okay, if we combine the gravitational force and the definition of force of mass times acceleration due to gravity, here's what we find out. The acceleration due to gravity is going to be equal to the gravitational constant times m divided by r squared. This gives the magnitude of the gravitational acceleration at a given distance from the center of the Earth. And if we look at this next table, we were going to see the acceleration due to gravity for various altitudes above the Earth's surface. So if you're looking at an altitude of around the mean of the Earth's surface, this is going to be your acceleration due to gravity. If you go up 8.8 kilometers, say at Mount Everest, this is going to be the acceleration due to gravity. If you go up, over, let's see, would that be over 4 times? 3, 4, 5. Yes, it would be. Highest crewed balloon, you're noticing that the gravitational constant is beginning to drop. If you're 400 kilometers above, then you are measuring it at 8.7, so you're really starting to see a drop. If you are at the altitude of a communications satellite, you're experiencing very little acceleration due to gravity by comparison. So the calculated acceleration due to gravity will differ slightly from the measured value of g at any location. Therefore, the calculated gravitational force on an object will not match its weight for 3 different reasons. Earth's mass is not uniformly distributed. As you can see here, the density is going to change as you move from the inner core to the outer core to the mantle. Earth is also not a sphere. Let's see if I can find the picture. It's approximately an ellipsoid. It does bulge at the equator, flattened a little bit of the poles. The equatorial radius is greater than the polar radius. And therefore, a point at the poles is closer to the dense core of the Earth than a point is on the equator. And that's one reason that the free fall acceleration g increases if you were to measure it while moving at sea level from the equator towards the north or south pole. You're actually getting closer to the center of the Earth if you move up that direction. And the other reason is that the Earth is rotating. The rotation axis runs through the north and south poles, and an object located on Earth's surface anywhere except at these poles must rotate in a circle around the rotation axis, and thus must have a centripetal acceleration directed towards the center of the circle. And that acceleration requires a centripetal net force that is also directed towards the center. So you got several different things going on there. So, difference in gravitational force and weight due to rotation at the equator. The normal force minus mass times acceleration due to gravity is going to be equal to the centripetal acceleration. Then gravity is going to be equal to the acceleration due to gravity minus omega squared r. Let's go back. All right, so we're going to analyze a situation in which a crate of mass m is on a scale at the equator. Right there. So a free body diagram for the crate shows that the two forces on the crate, both acting along a radial r axis that extends from Earth's center. The normal force on the crate from the scale is directed outward in the positive direction of the r axis. The gravitational force, represented with its equivalent m times acceleration due to gravity, is directed inward because it travels in a circle. As the Earth turns, the crate has a centripetal acceleration a directed towards the Earth's center, just what you see here. We know this acceleration is due to omega squared r, or equal to that, where we've got the angular speed and the circle's radius. We write all of that. This is what we come up with. So the measured weight is equal to the measure of the gravitational force minus mass times the centripetal acceleration. So the free fall of acceleration is equal to gravitational acceleration minus centripetal acceleration. So it's a fact you probably didn't know when you got up this morning, and now you do. So shell theorem also means that a uniform shell of matter exerts no net gravitational force on a particle located inside it. So forces between elements do not disappear, but their vector sum is going to be 0. And let's find the gravitational force inside a uniform density Earth, solid sphere, not a shell. So you've got an object, and you've got the force on that is the gravitational constant times the mass of that object times the mass of the inside the shell. divided by r squared. So with that, we have to describe the situation a little bit better, if it would work with me here to do that. So we've got a capsule of mass m falls from rest through a tunnel that connects Earth's south and north poles. When the capsule is at a distance r from Earth's center, the portion of the Earth's mass that is contained in a sphere of that radius is m sub ins, or inside. So if Earth's mass were uniformly distributed, the gravitational force acting on a particle would be a maximum at Earth's surface and would decrease as the particle moves outward away from the planet. If the particle were to move inward, perhaps down a deep mine shaft, the gravitational force would change for two reasons. It would tend to increase because the particle would be moving closer to the center of the Earth. It would tend to decrease because of the thickening shell of material lying outside the particle's radial position would not exert any net force on the particle. So to find an expression for the gravitational force inside a uniform Earth, there's a particular book here that has a plot that says three explorers attempt to travel by capsule through a naturally formed tunnel that goes directly from the South Pole to the North Pole. The capsule, when it has fallen to a distance r from Earth's center, at that moment, the net gravitational force on the capsule is due to the mass inside the sphere with radius r. The mass enclosed with a dashed line, not the mass in the outer spherical shell outside the dashed line. Moreover, we can assume that the inside mass is concentrated at a particle at the Earth's center. Thus, we can write the equation such as this. We know what the mass inside is if we know what our radius is and the density is. And substituting this expression into equation 1317 gives us the magnitude of the gravitational force in the capsule as a function of the capsule's distance from the Earth's center. So that's neat. If you go through and if you notice in that particular equation, this, and this are all constant. So if we write them as a constant, then this is basically a function that is being multiplied by a constant times the variable, that is the independent variable. That means an object that drops through Earth oscillates in accordance with Hooke's law. It is proportional to the distance that is removed from the center. So gravitational potential energy is a property of a pair of particles. We can't divide it up and say how much of it belongs to each particle in the pair. We often speak as of the gravitational potential energy of a baseball in the ball-earth system. And we get away with that because the energy change appears almost entirely as kinetic energy of the ball. We don't see much going on from the Earth, so we'll ascribe it all to the baseball and be done with it. And that only holds true for systems where one object is much less massive than the other. Gravitational potential energy for a two-particle system is basically the U is equal to minus G big M little m over R. And that value is negative and approaches zero for R running to infinity. And the gravitational potential energy of a system is the sum of the potential energies for all the pairs of particles. So if you've got particle 1, particle 2, particle 3, if you want to sum together all of the potential energy, then you have to take it between each of those particles. Gravitational force is conservative, and the work done by this force does not depend on the path followed by the particles. It's only the difference in the initial and the final positions of the particles. So since the work done is independent of the path, so is the gravitational potential energy change. So the change in the potential energy is going to be the change in the final minus the initial, and that is going to be the same as minus the work. Newton's law of gravitation can be derived from the potential energy formula by taking the derivative, which if you do that, that's an interesting exercise. For a particle or for a projectile to escape the gravitational pull of a body, it must come to rest only at infinity, if at all. So at rest at infinity, it has no kinetic energy and it has no potential energy because R is dead for all intents and purposes infinity. So the sum of the two must be at least 0 at the surface of the body. So you put the two together and 1/2 mv squared plus this is equal to 0. If you go through and you solve that, then you find that the velocity is going to be equal to the square root of 2gm divided by r. If you've ever heard of escape, the escape velocity, this is what we're talking about. So rockets, if you've ever wondered why all of our rocket launches, at least most of them, take place in Florida, we like to launch eastward. That's a safe place to do it. Hardly anybody out there in the ocean. And we also take advantage of the Earth's rotational speed. In other words, it's going to give you a little bit of a push. So that's why the rocket facility is where it is. You've got different escape speeds here for different radius and different mass. You can go through the computations, and obviously you can see some major differences here, and the more massive and bigger the radius, they start to have an effect on the escape speed. The time you get to a neutron star, forget it. So you move a ball of mass m away from a sphere of mass big M. Does the gravitational potential energy of the system of ball and sphere increase or decrease? Well, let's go back and let's take a look. There's the formula for potential energy. We're increasing this. The masses don't increase. But as this increases, what happens here to that expression? As this increases, the denominator gets smaller, and you're taking a set number up here and you're dividing it by a smaller number, which means it's going to get an even bigger number. Let's see, do I have that right? So we have, okay, so we increase this distance. If we increase this distance, then we're dividing by a bigger number, which means if we're dividing by this by a bigger number, that means that this actually does begin to get smaller, but since it's negative, we're going from a much larger negative number to a much smaller negative number, so it increases. Sorry for my pause there, but is positive work or negative work being done by gravitational force between the ball and the sphere? Well, that change in kinetic energy is going to be minus work. So we're going to have negative work. So the motion of planets in the solar system was a puzzle for astronomers, especially a curious motion such as what you see here, where it kind of looks like it loops back on itself. Johannes Kepler and Tycho Brahe were working on the problem. Mr. Brahe there was taking several measurements. Kepler said, hey, maybe I can come up with some laws of motion. Sure enough, he did. And this is a part of what he came up with. We've got laws of orbits. The first one here, all planets move in elliptical orbits with the sun at one focus. An elliptical orbit, basically you have the difference there between that and a circle is going to be that you have 2 points, 2 foci in a circle, in an ellipse, as opposed to a circle where basically the 2 foci become 1. So the orbit is going to be defined by its semi-major axis A and its eccentricity E. If your eccentricity is 0, then that means you've got a circle. And for Earth, you're looking at an eccentricity of 0.0167. Very, very close to being a circle. Number 2, the laws of areas. A line that connects a planet to the sun sweeps out equal areas in the plane of the planet's orbit in equal time intervals. In other words, the rate of the change of the area with respect to time at which it sweeps out is going to be constant. It's equivalent to the law of conservation of angular momentum. Number 3, the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. If you work specifically with, I believe it's years, and work with astronomical units, as far as the semi-major axis is concerned, you can come up with an exact. It's no longer, you can come up with an exact equation to do that with. Mathematically, if you replace R with A for elliptical orbits, you can see how these two are associated with each other. So satellite 1 is in a certain circular orbit around a planet, while satellite 2 is in a larger circular orbit. Which satellite has the longer period? How long is it going to take to go around? So satellite 2 is going to have the longer period. The greater speed is going to be satellite 1 because it whips around a little bit more quickly. You can think about planets in that sense. It's going to take Jupiter much longer time to make an orbit around the sun than the Earth would. The Earth is going to travel faster. Relating the centripetal acceleration of a satellite to the gravitational force, we can rewrite as energy. So the kinetic energy of 1/2 mv squared is going to be equal to g mm over 2r. So that means that the kinetic energy is going to be equal to the negative of the potential energy divided by 2. Total mechanical energy, if you sum the two together, be equal to minus g mm divided by 2r. So the total energy E is going to be the negative of the kinetic energy. For an ellipse, you're going to substitute A in for R, and therefore the energy of an orbit depends only on a semi-major axis, not its eccentricity. And all orbits in figures 13 through, or in figure 1315 have the same energy. All of these have the same energy, but their eccentricities are going to be different. And this is going to be a plot of the satellite's energies versus the orbit radius. You can see the kinetic energy is being positive, but it's going to start to die out as the R increases. Potential energy and total energy are going to be negative. In the figure here, a space shuttle is initially in a circular orbit of radius r around the Earth. At point P, the pilot briefly fires a forward-pointing thruster to decrease the shuttle's kinetic energy and mechanical energy. Which of the dashed elliptical orbits shown in the figure will the shuttle then take? Since the energy is decreased, it's going to end up taking orbit 1. And is the orbital period T of the shuttle, the time to return to P, greater, less, or the same as the circular orbit? So since the semi-major axis has decreased, so the period decreases. So if you look at period decreases, that's going to be directly proportional to the semi-major axis if you replace R with A. Now, the general theory of relativity is going to attempt to describe gravitation. And its fundamental postulate is going to be the principle of equivalence. In other words, gravitation and acceleration are basically the same thing. It depends on your reference frame as to what you call which. So take an experimenter inside a box, and he feels some kind of acceleration going on in there. But if he can't see through it, he has no idea if he's out in space or if he is somewhere on the ground. That frame of reference doesn't matter. It's going to be the same thing. So then the gravitational acceleration must have, well, they're equivalent. Doesn't matter. We're looking at the same effect either way. So space or space-time is curved. If you look at A and B, paths that appear to be parallel along the surface of the Earth. Let's see if I can zoom in a little bit. Or falling towards the Earth's center, actually converge. If you can look at it this way. You can see why by stepping outside the curved Earth, but we can't step outside of curved space. And light bends as it passes by massive objects, and this is called gravitational lensing. In extreme cases, we observe light coming from multiple places or bent into an Einstein ring. This was also observed, I believe, in a solar eclipse somewhere around 1919, 1920, to try to, it was used actually to try to prove whether or not Einstein's theory about relativity was correct, and indeed it was. The source of gravitation is still unclear. Is it purely an effect of curved space-time? Is it a force between masses? Is it due to fundamental particles, the graviton, which would carry the gravitational force? We don't know. But we're always looking to try to find the answer. And here is the summary at the end of the chapter. Next time, we will go on to chapter 14.